The next step in our investigation of CoCoALib is looking at the manual itself. The manual, as I said, it is difficult to read as a beginner, but I thought that this was interesting to see this page, which is a bit of the picture of what's inside CoCoALib. So here you see the main points, the main objects you can work with, like matrices, modules, numbers, things related with Grosvenor basis or rings. And so we have some titles which collect the main blocks in CoCoALib. And then in these you see the structure, like in this case we see ring LM input, which is something related with ring LM, ring FP, and all the different implementations we have for ring FP. And so you get the picture just at looking at this page. If you're searching for something, you need to be online. You can write something here, and then you have a Google search restricted to this part of the website. So I want to show you the structure of the documentation, and I'm not going into the details because as we said, the easiest way to look at things is to start with CoCoA is starting from the examples. But I want to show how this is structured. So let's see, for example, numbers. Numbers, you see the kind of files or parts of the files we have, so big int and big rat and machine integers, and then the operations for big int and big rat, which are written outside, or the interval arithmetics and so on. So I want to show you this because random is something that you might want to use in your program. And so what do you have in a manual web page? You have the index of the page, so you can see what is available. And then you have a list of examples that you might want to consider to see how this object is used. And maybe some explicit examples like this one. So a bit differently from CoCoA 4, you create a random generator. Like in this case, you can make a specific random generator that produces a long between -9 and 9. And then with the function x value of this random, you get different values. This is if you want to get your own so that you can control what your random values are. Or there is also a global random source so that you have this random generator and you can extract from it whatever values. You might be surprised by this, but for debugging, it is very useful to have your own random generator so that you can reproduce exactly the same random sequence. This is essential for debugging. So when you are working with random numbers, probably it is much more convenient to use this global random number generator. But if you are investigating your own code, it might be better to have your own random generator. All for this, but it's something that you might need. So I thought of telling you this thing. Then, of course, the core of CoCoA relies on rings. So we see this is the manual for ring. And this gives you some examples for the rings and shows you the structure that is inside. So as a user of CoCoALib, you don't really need to know about inheritance of classes in C++. But we developers, we use it a lot. So indeed, we have a very interesting construction of the rings, so that we have a very general implementation, abstract implementation of a ring that has the operations you expect in a ring, I mean algebraically. And then a ring might be ring ZZ or a fraction field, and there's a specific implementation of fraction field. You have the rationals, or you can have a generic fraction field of any ring, which is an integral domain. And the same way we have a quotient ring. And as an example of a quotient ring, we have Z modular number, so ring FP for the prime numbers. And then we have polynomial rings, which are the core object in CoCoA. And we have an implementation for univariate and multivariate polynomials, which are, just to give you an idea of what's inside. In the univariate polynomials, there is a specific implementation, which is a dense representation. That means it is a vector, and in each slot, you have the coefficient of x to that power. And we have the sparse polyring, where the elements are linked list, where we have a monomial with a link to the next monomial with a link to the next monomial. So this is to show you the organization of CoCoALib. Let's go back, and here we see the ring elements, which are really the objects you probably will use most. And again, here you see that there are, this is a special page for ring elements because they are so important. And so we, even though the implementation of the abstract classes together with the rings, we made an explicit page because we wanted to show in one page all the possible operations you can do on ring elements. What do I mean, all the possible operations we can do? As I said, we have all kinds of rings. And so we have operations which work in general in any ring, like asking if a ring element is 0 or is 1, or I want to do the sum of two ring elements or the product of two ring elements. But what happens is that if I have, say, a fraction field, then an element in a fraction field is represented with a numerator and denominator. So we have the functions num and den, which are only in the case that ring element is an element of a quotient ring. Of a fraction field, sorry. In the quotient ring, we have a representative, like there is an example here. If r is -3 and r -10, then this function will give 7 as the canonical representation for the class of -3. What is interesting for us is especially ring elements of polynomial ring. And remember what I just told you, that we have polynomial rings and sparse polynomial rings, which I mean multivariate rings, in fact. So operations on polynomial rings are operations which apply to any kind of polynomial. So I'm asking if if a polynomial is a monomial, for example, if it is an indeterminate, or if it is irreducible, or if what was the number of the terms, or the degree, or if it is, was its constant coefficient in the polynomial, and this kind of operations which work for any kind of polynomials. But if I have multivariate polynomials, then there are other operations I want to do, like LPP, the LF, the leading form. You want the homogeneous components in this multivariate polynomials. We have the concept of the weighted degree instead of the normal standard degree, the normal remainder that we know very well now, the homogenization of a multivariate polynomial. So you see that there is a class of operations that are specific for multivariate polynomials, which are not general for any polynomial, and also the constructors for monomials, because we saw that a power product lives in a monoid, and so if I want to make it become a polynomial, I have to say in which polynomial ring I'm going to send it. An interesting part of this, here it is, the fast, ugly, and unsafe operations on raw values. I talked to you about this in the last lecture, and there are operations I can do without doing any check at all on the compatibility of the objects, if it is meaningful to add two ring elements. If they're not in the same ring, it doesn't make sense usually. So, but if I want these operations to be super fast, I don't want to make the controls to check if they are compatible or not, then I can use this very dangerous kind of syntax. I told you that there are these kind of functions, and this is a place where you find them. Be careful. Don't use them if you can avoid it. So go back here. I talked to you about the monoids. So here they are, PP monoid. So this is the monoid of the variable of the power products, and we have a special type class for them. And again, here we have inheritance because we have different implementations depending on what kind of operations you want to do. Let's see, I should have, yeah, here. So there is a PP monoid which stores the exponent vector, which is the most natural way of thinking of a power product, the exponents. And another implementation which stores the order vector. That means in Grosvenor basis computations, we saw that we use orderings. With the orderings, you can represent an ordering with a matrix. And so to know how to sort a polynomial, you have to make the product of this matrix with the exponents. That means that if you want to do it many times to sort polynomial, which is every time you do an operation, it is very expensive if you have to multiply the matrix with the exponents every time. So we have an implementation that stores, instead of the exponents, stores the order vector. So that this kind of implementation is very good for ordering polynomials is not very good if I want to see if a PP monoid divides another PP monoid, because I don't have the exponents readily accessible. And then we have also an implementation with both of them, which is very good because I have the best of the two worlds, but of course it takes twice as much memory. So you can choose if you need some specific efficiency in one of these fields. And there is, in the case of the PP monoid, we have orderings, and so here we see the operations we can do. This is inside, sorry, the summary of functions for PP monoid LMs, which is inside, it is actually in the same file, defined in the same file as a PP monoids. So these are the general operations. You see here, there is ordering. So I can ask if a PP monoid LM is smaller than another. And this is actually used when you use these power products in the implementation of a ring, polynomial ring, because we keep always the polynomial sorted. So you have to compare the power products inside the support of the polynomial. And here are the operations that you expect to do with the power products. Of course, you don't have addition in this case, but you have the product. You have the division if possible, of course. If it is not possible, you will get an error. So if you divide x by y, this is not a power product, so you get an error. If you divide xy by y, you get x. And then you have the colon, which is similar, can be handy, which divides what it can. So if I divide x by y, I just get x, because I cannot divide by y. Formally, it is the first power product divided by the GCD, or the two power product. And then you have the GCD, least common multiple, the radical. You can have a power. You can ask if two power products are coprime, if one divides the other. You can have this constructor so that P gets the value of the product of P, PP, and PP1. And here you have the exponent vector. Or no, in this case, it is the exponent, the ith exponent, or you can get the exponent vector, or you can have the exponents but written as big integers in case you expect in your computation you have power products whose exponents can get huge, bigger than the maximum you can get as a machine integer. That's unusual, but so that you know, you can also have these huge exponents in CoCoALib. Okay, so we had an idea of what is inside CoCoALib, and now we are ready to investigate and get into the examples themselves. Okay, see you in a bit.